So thanks for the introduction and thanks for the organizers for the invitation to speak. So the title of my talk today is on p-Isogenies with G structure. And this joint work in progress with Keerthi. Okay, I've given a talk about this before and I promise that this time we are actually writing it out. So hopefully the paper will be out soon. Okay, but let me, to kind of motivate like the question of like p-Isogenies with G structure, let me mention something which I think you'll see Ming Jia will talk about this a little bit more tomorrow. So if you sort of start with Shimura datum, and let's say you have some compact open, then we will see, I mean, she will explain tomorrow that we have this Igusa stack diagram. So you consider the Shimura variety sort of with prime to p level Kp with this sort of compact open. Gx. Say take the diamond of this. So there's the Hodge-Tate period map to the flag variety. Let's say G mu. And it's sort of fits into this Cartesian diagram that she'll explain. This X Gx is Kp and Bungie. So I mean, she'll sort of explain more, I mean, this setup tomorrow. But the point here is that, so let me, of course, attribution, of course, this is due to Ming Jia. And this paper, for the paper of Daniels, Van Hoften, Kim, Zhang. So she'll explain, I mean, in what situations that they've constructed this diagram and under sort of which conditions. And so, I mean, the motivation of this, of course, is that, you know, with this diagram, like you will see tomorrow, she'll explain that, so with this diagram, together with like this sort of geometric local Langlands correspondence, we've sort of proved sort of very interesting results about the sort of cohomology of the Shimura variety. So this has consequences for the cohomology of the Shimura variety. Okay, so that's all I'm going to say about this. So, I mean, I guess the motivation sort of comes from tomorrow's talk. But I think the point here is that, so very vaguely, like what is this Igusa stack diagram? So let me just say, this Igusa stack is somehow what you obtain by sort of quotienting. So the way to sort of get the thing at the bottom is by quotienting. So let me just say this xkp is obtained, this is very roughly, by quotienting by sort of p power isogenies, preserving the G structure. So that's somehow like roughly what this object is. And I think you'll see tomorrow that, I mean, they sort of don't work with this sort of directly, this sort of p power isogenies, or sort of in this, they have some trick to sort of get around this, to sort of work with this p power isogenies. But the point here is that, roughly speaking, if you sort of wanted to generalize their constructions, you will sort of really need to have some understanding of like what p power isogenies really are. And I think there's maybe one observation, if you sort of just think kind of naively about p power isogenies, is that this notion of an isogeny is somehow like very closely related, not to this sort of G, but really to the sort of underlying thing that you're parametrizing. So let me just say it's sort of the notion, or I should say this p power quasi-isogeny. So the notion of a quasi-isogeny is somehow something that's very tied to this notion of the abelian variety. So somehow you sort of always need to refer to the underlying abelian variety. So notion of quasi-isogeny dependent on the sort of underlying abelian variety. So I mean, even in what they prove, like somehow there is a reduction to a sort of Hodge type situation. So you require some conditions on the Shimura datum such that you can relate it to an abelian variety. And so the point here is that somehow like the notion of quasi-isogeny that we are working with so far is very dependent on understanding this underlying abelian variety. Okay, but the point here is that you want, but of course, I mean, the point here is that there's sort of has been advancements in like the study of Schumann varieties that we can move beyond situations where you're sort of tied to this abelian variety. And I think in such a situation, you really need to sort of make a sort of meaningful understanding of like what this notion of a p-power quasi-isogeny preserving G structure is going to be without referring to the abelian variety. So maybe I should say we need to understand this in an sort of abelian variety free manner. So the reason why you should do this is, I mean, because for instance, there are situations where we now have an integral model of the Schumann variety. So there's like hope to sort of get this kind of diagram, but in which, you know, there's no abelian variety. So for instance, I think there's a sort of forthcoming work. So this is forthcoming work of Mada Pussy and so my collaborator and Alex Lucas. So what they have is that they've shown that if you are a pre-abelian type Schumann variety, so I mean if you're not sort of very into this classification of like which Schumann data is pre-abelian type and not pre-abelian type, maybe I should say that the point here is that there's more things which are pre-abelian type, as the name suggests, and one of the things which are pre-abelian type but not abelian type is sort of general sort of DH type Schumann datum. So this is sort of one class in which you now sort of have an integral model, integral models. So DH datum. So that's one class in which now we sort of have an integral model in which we sort of hope to produce this Igusa stack as well. And the other one is this work of Baker, Shankar, and Zimmerman. So I spelled his name correctly. Which is, if you sort of allow a sort of very explicit, I mean a very inexplicit large prime P, then they also show that there is an integral model. So integral model for so exceptional type Schumann varieties. So I think both of these works sort of motivate the reason for us to sort of move beyond. There's a notion of an isogeny attached to some abelian variety. So that's basically the motivation for why we sort of want to consider this general setup that I'm going to do now. So let me say a little bit about the framework which I'm going to be using. So the framework, of course, is in this sort of setting of like F gauges. So why do we sort of use this framework of F gauges? Is because, I mean, the point here is that, I mean, if you believe, I guess, the Lean's formalism of like Schumann varieties, like Schumann varieties should be moduli of motives. But of course, I mean, we don't have like a sort of a good understanding of, I mean, there's no good theory of motives, but we do have these realizations of these motives. And one realization, of course, is the sort of prismatic realization. So this F gauge is a kind of, maybe I shouldn't say prismatic, it's really some kind of symptomic realization. Or at least the way to sort of think about it is really as some kind of symptomic realization of the underlying motive, if there was indeed this motive attached to it, or this G motive. I guess it should be the bold G. Right. So I'm not going to sort of define this because this is going to take too long. But if you sort of haven't seen this this theory of F gauges before, the way to sort of roughly understand this is that it really is a sort of generalization of the sort of crystalline realization of the F motive, or sort of the G motive that we've sort of seen before. So let me just say roughly this generalizes this F crystals. So these are sort of crystalline realization. We say F crystals with G structure. That you sort of see in characteristic P. And so one way in which we can sort of really make this this analogy kind of explicit is that in a setting where we do have access to the abelian variety, like we expect that this F gauge is related to some cohomology, for instance, the prismatic cohomology of the abelian variety, and that's shown more or less by the work of like various people. So let me just say, one way to sort of really kind of push this analogy a little bit is that you recall that, for instance, if I have a relative abelian scheme, and X is a scheme over characteristic, say Fp, then we know that the crystalline realization of this is really the sort of R1 F cris of, say, the structure sheaf of A. Let's say you're sort of working over this base, which is Zp, for instance. So this is the sort of the crystalline realization of this the motive attached to this abelian scheme. So this is the F crystal attached to the abelian scheme. And the work of various people. So let me just say, like, so this is the sort of F crystal. So this notion of F crystals, of course, is down to like many people. For instance, like Berthelot, Breen, Messing, Grothendieck. So I'm not going to write the names of the people who sort of studied this thing in this F crystal in this setting. But the notion of an F gauge. So this is due to Barth and Lurie. This is due to Barth and Lurie. But sort of even before then, or sort of more or less at the same time, this generalization of like what is this motive that's attached to this abelian scheme in this sort of mixed characteristic setting where you're interested in this symptomic realization. This is this symptomic realization. Sorry, I think this is. Symptomic realization. Sort of due to various people. So I think it sort of started more or less in the work of like Anschutz, so there's also a related work by Subodhip Mondal. And the sort of strongest result of this like symptomic realization was sort of proved by this theorem of Gardner-Matepussi, which I will explain. And it sort of explains why it sort of makes sense to work in this setting, just because like they showed that there's really a sort of equivalence of categories that like makes this the sort of correct object to study. So what did they prove? Their theorem is the following. So this is, sorry. This is in this paper of Gardner and Matepussi. But I think this framework, I think, was really sort of conjectured, I think, variously by Akil, Matthew, and I think maybe Drinfeld. Okay, so I think they really sort of conjectured this thing, maybe. And the reason why this is the sort of correct framework, like why this F gauges is the sort of correct framework, is because we know that if I'm working the setting where R is a sort of pre-complete ZP algebra, so with some kind of finiteness condition. So essentially this the sheaf of differentials, sorry, gamma 1 of sort of mod P is sort of like finitely generated. So somehow the point here is that I allow things which are sort of finite type, or maybe sort of perfections of things which are finite type on the mod P fiber. So that's somehow some kind of finiteness that we sort of require this ring R to have finitely generated. So this is the condition on the R. But under these conditions, there's an equivalence of categories between like p-divisible groups over R. And what I'm going to say, certain subcategory of these like F gauges. So I didn't explain what an F gauge is, and I also will not sort of explain fully like what object is going to appear on this right-hand side. But essentially, these are sort of like certain kind of vector bundle F gauges with certain Hodge-Tate weights. In 0, 1. So there, to an F gauge, you can sort of associate the notion of a Hodge-Tate weight because, let me say, this notion of Hodge-Tate weight is because the idea is that this F gauge is, some kind of cohomology. So in the case of, some kind of, it should sort of recover, like for instance, this F crystal. It should also sort of recover the de Rham cohomology or the Hodge cohomology of the abelian scheme. So if you're in that kind of setting and you expect this kind of like relationships between like all the various cohomology theories, this notion of Hodge-Tate weights comes about because somehow you can sort of relate this F gauge or this vector bundle F gauge to the Hodge cohomology. Hodge cohomology. And so this thing about like Hodge-Tate weights being in 0, 1 is of course the same thing as sort of saying that like the sort of Hodge cohomology, like those are the sort of graded pieces that you see. And so in the sort of general setting of like abelian schemes, like this Hodge cohomology should of course have this grading in 0, 1. Okay. So, I mean, the point of sort of saying this very roughly is because like this setup is the one that we are going to use to replace the notion of an abelian variety. So instead of trying to study the abelian variety over the Shimura variety, which sort of is the reason why you're sort of stuck in the Hodge type situations, you move to the setting where you're interested in studying this symptomic realization instead. So you just study this object instead of trying to sort of study the abelian variety. But of course, I mean, once you sort of move to this setting, then the whole point is that it's very unclear like what it means to be an isogeny. Remember, the sort of motivating question is to ask, like when do I have an isogeny? Like what does it mean to sort of have a p-Isogeny in this setting? So let me just say this, let's just say in this framework, what we're interested in is sort of we replace an abelian variety with, let's say, some kind of F gauge with G structure. So I'm not going to, again, I'm also not going to give like the sort of precise definition of this. So there's a name for this that was sort of given by Gardner and Manapusi. So they call this object. So there's always a group G. You always have to, I mean, if you're sort of interested in something which has G structure, like the group must appear. So there's a group. And more than that, I'm sort of looking at an integral model. So G, so I guess this G here is a kind of GQP object. So I'm interested in this sort of curly G, which is a reductive model of the GQP. And I mean, there's some prescription on what the weights should be. So, and the weights should of course be given by the Hodge co-character, the same mu that you sort of see up there. But of course also extended integrally. So I need this kind of integral data. So both of these things are sort of over ZP. And if I sort of have both of this data, then what I'm replacing with is this F gauge with G structure is what's in the paper of Gardner and Manapusi they call a G mu aperture. So there's some analogy that one is trying to draw with this name, But let me not go into the... Okay, but I mean, the point here is that if we replace abelian variety with this notion, then what we are going to do now is explain, I mean, in this notion, like what is an isogeny? Okay, the last thing which is missing is that this is we sort of call this the G mu apertures, but of course, you can look at the stack of these objects. So let me give a name to the stack of these objects. That's what we call BT infinity is G mu. So this is the stack of this G mu apertures. Okay. So the idea now is I'm going to sort of try to construct like a certain isogeny stack or quasi-isogeny stack that lives over this stack of G mu apertures. So the terminology, this BT is supposed to sort of be reminiscent of like the stack of p-divisible groups. So you're supposed to think that, you know, in a situation where this G is GLN and this mu is like, say, so let me just say, if this G is GLN and this mu is like 1, 1, 0, 0, then we GLH, so, and this is R, then this is supposed to be the stack. It's the stack of p-divisible groups with height H and rank R. So there's a very strong analogy between this stack of apertures and the stack of p-divisible groups. So just as over p-divisible groups, I mean, we have the notion of an isogeny between p-divisible groups. Then we sort of want to now define a notion of quasi-isogeny or quasi-isogeny living over the stack of like G mu apertures. Okay. So first, I mean, let me explain something which is not the answer, but which I think sort of motivates a little bit like why the structure of the answer is the way it is. Okay. So let's go back, because we sort of want to draw this analogy between like the symptomic realization and this crystalline realization. So in the crystalline case, like what is a quasi-isogeny in that kind of setting? Well, you might say, okay, like it's a quasi-isogeny if, you know, when you pass to the iso crystal, in other words, when you invert P, that's an isomorphism. So maybe let's just say in the case of an F crystal, what you see is that we ask to be sort of a quasi-isogeny is what you get when you have, let's just say, so roughly, is what you get when you invert P. So in other words, you form the F isocrystal. And to be quasi-isogenous is the same, is to ask for an isomorphism of this underlying, this doesn't make sense. Quasi-isogeny is, sorry, where's the duster? Yeah, so maybe I should say a quasi-isogeny is that you have isomorphic F isocrystal. Isomorphism of F isocrystals. So, I mean, with this kind of understanding, maybe you might think, okay, so you just look at this G mu aperture and then you do something which sort of formally inverts P again, and then you can ask for some kind of isomorphism of this object where you sort of invert P. But the point here is that for our purposes and sort of really for sort of understanding this construction, like it's sort of not so good to sort of work with the notion of quasi-isogeny. So we can consider such a notion. And again, you sort of, i.e. you sort of invert P, and then you ask for isomorphism. But this is sort of not so good because really, like if you sort of think about like what's happening to like the space of all quasi-isogenies, this is not good. Sort of for geometric reasons, because if you think about what's the space of all quasi-isogenies, go for geometric reasons. Like if you think of like this, I mean, just even in the setting of like a billiard writing, you think of like this case of like all quasi-isogenies to like one fixed guy. The issue is that, I mean, we know that quasi-isogenies are like they are rigid, so you can always kind of lift them over like nilpotent thickenings. And so that implies that the deformation space is too large. So you somehow want to get something, an object which sort of works very well. I mean, in the setting of like classical algebraic geometry, of course, I mean, in like this p-adic setting, maybe it's still fine, and that's kind of one of the reasons. But for geometric reasons, this in sort of classical algebraic geometry, this space of quasi-isogenies has a deformation space which is sort of too large. Too large. And in particular, I mean, this sort of too largeness means that you don't, you sort of can't attack questions about like representability just by sort of thinking about the quasi-isogeny. So in other words, you sort of can't show. Maybe I should move this second one up. So I think you sort of can't show representability results maybe. Sort of by directly contemplating this quasi-isogeny or this kind of definition. So directly contemplating this. Okay. But so because of that, I mean, like let's kind of think about like what was the fix, at least in the case where you're like an actual p-divisible group and you are looking at like the space of quasi-isogenies. So if you recall, like in this construction of Rapoport-Zink, like I mean, they think of like spaces of quasi-isogenies with like one fixed guy. Like how did they sort of show us this kind of representability results? Well, I think the idea is that there is some filtration. They sort of had a filtration on this notion of a quasi-isogeny, basically by the denominator. So by the degrees, the sort of powers of p that you sort of apply to the quasi-isogeny and its inverse to sort of make it an isogeny. So maybe let me just say that in the classical case, what we did was we sort of filtered by the degree, or maybe I should say power of p, to make it an isogeny. Make a quasi-isogeny. An isogeny. Okay, and then this idea of like sort of filtering allowed you to sort of really produce like pieces of the space which are representable, and then after that you sort of take the limits. So you get something which is sort of a pro object, which is built out of things or some formal objects, such that each piece is sort of like, say, finite type, for instance. And this produces a notion. This gives a sort of well-behaved let me say, maybe stratification on the space. And in particular, sort of in the setting of sort of formal geometry, this is sort of better behaved. So better for the formal geometry. Okay. And the way to sort of think about, like how to sort of generalize this, I mean, there's this P, so like, I mean, again, this everything I've sort of written down here is somehow like implicitly appealing to the p-divisible group that's sort of underlying this space of quasi-isogenies. Otherwise, like, it sort of doesn't make sense to sort of say all these things that I'm saying. So, but at least, I mean, like, there's a sort of toy model for like what's happening here, which is, let's kind of think about for like what's happening here, which is to sort of think about like the space of sort of H by H matrices. So let's call this MH. And what's kind of happening here is that when we sort of think of a quasi-isogeny, I want to say that sort of, so a quasi-isogeny here, somehow on the generic fiber, I want to say that I'm looking for a kind of QP point of this MH, which I want it to be an isomorphism after you invert P. So I want it to be somehow not just a QP point of the space of H by H matrices, but I really want that somehow on the generic fiber, I want this thing to actually land not in here, but really in like GLH. So somehow invertible on the generic fiber. And to say that, you know, it is an honest isogeny. So like when you sort of get an honest isogeny, it is when you get a point, which is, you know, you get a QP point of this GLH, and then you can ask yourself, you know, like GLH kind of embeds in this space of H by H matrices. Like when does it extend to a ZP point of this MH? So an isogeny is maybe, let's call this G in GLH QP. And an honest isogeny, sorry. No, there's no framing object. I mean, this is just kind of some kind of motivation. So there's no framing object. I'm not talking about a framing object right now. Okay, but I mean, I'm trying to sort of motivate like the definition that I'm going to do next. So I'm trying to sort of like think of this kind of like toy model that we can sort of use to kind of understand, you know, like what's the difference between like an isogeny and this kind of like filtration. So, for instance, I mean, I'm going to say, for instance, like thinking of a quasi-isogeny is somehow thinking of like some sort of rational points. I mean, not just QP, but maybe I sort of really think of like a sort of WK point where K is a perfect field. Oh, sorry, 1 over P point where K is a perfect field. And I'm asking for an isogeny is really asking for, say, WK point of this space of H by H matrices. So I'm allowing it to extend, but I'm allowing it to extend somehow with this, not necessarily sort of being in the group, but sort of extending it into the sort of bigger space of H by H matrices. And the point here is that, you know, this thing can sort of be made slightly more rigorous in the sense that if you're really sort of analyzing what's happening on like the level of F isocrystals or so evaluated on K perfect fields, then somehow this really recovers, you can sort of really formalize that, you know, a quasi-isogeny really is sort of given by one of these points on like the, as an action on the F isocrystal, and then an isogeny is sort of given by this, this WK point, which sort of extends, like you sort of really get a map on lattices exactly when you extend to a map on, when you extend integrally to a point of the matrix, space of matrices. So anyway, the point here is that like there is some kind of toy model that we can sort of keep in mind for what's happening, and that's kind of using this space of matrices. But really, I mean, like what I sort of want you to sort of see from this is that this gives you, so this is an example of what I'm going to call an isogeny model, or some kind of example. But the point here is that you observe that what happens is that you are looking for an object which is going to be a monoid. This is really a monoid for GLH. So the space of H by H matrices is a monoid for this group. And what you're asking for is that, you know, you're going to try to look for like generalizations of this monoid for the reductive group that you're going to sort of try to use to kind of like extend the point. So you're going to try to say that, like, you know, a quasi-isogeny is like some point when you sort of invert P, but an isogeny, or sort of like maybe isogeny with sort of like bounded denominator, is going to be like a certain point of like some monoid that sort of extends integrally. So you sort of want this is what we want in general. Okay. Okay, let me send this all the way up. Okay, anyway, the point of that toy model is that this toy model sort of tells us a little bit about like what's the general object that we are sort of looking for. And because of that, let me just give a definition of like, you know, in general, what kind of object you will be sort of looking for as to produce like a space of isogenies. So you'll be looking at an object which somehow generically, when you invert P, is going to be isomorphic to the group over QP, and which maybe when you sort of look at it as a sort of integral object, it is it sort of has an action of like this G on both sides, and somehow it's maybe some kind of monoid object. So maybe let me just write down as a kind of there's a definition that we use. So we call an isogeny model. No, sorry, this is bad English. So definition. So it's an X. So this is a, okay, I mean, I'm going to say scheme, even though the next example that I'm going to give is not quite a scheme, but X a scheme over CP is an isogeny model. If, let's say somehow over the generic fiber, you have something which is going to recover the group. So this is going to be isomorphic to GQP, and which has a sort of G cross G action, such that this, I mean, if there's a sort of G cross G action, then you can sort of think about like what are the sort of GP points or WK points of this scheme, such that this WK points, let's say WK. So again, K here is a perfect field. This thing is a disjoint union. So I want something that sort of, I mean, here there's this XWK is going to sit inside the set of K points with sort of P inverted. But if I'm looking at the points with P inverted, then that's the same thing as just looking at the points of the generic fiber. And I know that on the generic fiber it's sort of isomorphic, so I can sort of put isomorphism between this guy and GWK 1 over P. And I want to say that, you know, this sort of via this inclusion of like the WK points of this scheme, this isogeny model, this thing that you get is going to be some part of the Cartan decomposition, right? I'm supposed to be getting something like a GWK 1 over P, say P lambda prime, this GWK. So this is something that I want. I say it's sort of an isogeny model if, you know, it has this property that somehow on the generic fiber is isomorphic to G, and somehow we have this sort of G cross G action on the full space itself. That's that when you sort of consider the points, the WK points, you sort of have this nice decomposition that sort of picks up exactly like the sort of closed conditions on this like Schubert cells. Oh, sorry, yes. Of course. Thanks. So that's what we call an isogeny model. Yes. Yeah, I assume that it is flat, maybe. I mean, okay, this is a definition, and somehow like we sort of give examples of things, and they all turn out to be flat. Yes, sorry? Oh, yeah, of course. I mean, the point is that not necessarily. I mean, like like you can sort of have different isogeny models, but of course, like for some lambda. So maybe they should say so that this is true for some lambda. So I want it to be that, you know, that there are some lambdas such that like this WK point is sort of exactly going to give me the double coset decomposition for this particular lambda. But of course, I mean, sorry, what's that? But of course, there's a canonical choice. For us, there's a canonical choice of this, what this isogeny model should be. And that sort of comes from the fact, like that example above, that we want it to be a monoid. So we obtain these kind of examples of, or at least for us, like the sort of isogeny models that we could construct from this setting, all come from this Weinberg monoid. So we obtain. So essentially, for us, we don't obtain isogeny models outside this like situation for a Weinberg monoid. So we obtain these isogeny models from this Weinberg monoid. And I'm also not going to define this Weinberg monoid, but the point here is that the Weinberg monoid is, first, it is a monoid, as the name suggests. So this VG is going to be a monoid. This is a monoid for the sort of the group G, or a sort of slight enhancement of the group G. So it's essentially sort of the group. This T is a Cartan, or this sort of a quasi-split torus. Let's just say the Cartan in G. So it's defined over ZP. So all this is kind of integral objects. But when you sort of quotient out by this diagonal copy of the center, so it's a monoid for sort of the group G, or a slightly larger version. But it's sort of fine because what happens is that this Weinberg monoid, sort of by the sort of generalities of like what this object is, it emits a flat map. Let's call it map D. It emits a flat map to this. This is going to be it is isomorphic to AR, where R is the rank of this T-ad. But maybe I should say, I mean, like, what is this T-ad? As the name suggests, this is some relation to this this torus T-ad. And this is basically the toric variety for this T-ad, such that, like, every co-character, or every dominant co-character, lambda p, extends to a point of this T-ad. So let's just say this is spec CP, so lambda dominant. And somehow like this is sort of exactly the toric variety, such that you have this property. And the isogeny models say, for instance, with this lambda, this property that I always have this lambda prime less than lambda is going to be this like X lambda ad. It's going to be sort of produced by sort of taking the fiber product over this point of this torus. So there's a flat map, so this map is flat, and then you're going to sort of produce this object, which is also going to be flat over here, just by sort of pull back from this point over this toric variety for T-ad. So these are going to be our isogeny models. Okay. But actually, I mean, okay, since I should say, I mean, like, I sort of given this talk, and I always say it is the Weinberg monoid. But actually, the thing that we work with is actually not the Weinberg monoid. It's some slight variant of the Weinberg monoid, where essentially you're sort of trying to make the action of the center, sort of like get rid of like some extra action of the center. So, I mean, if you sort of look in the original construction of Weinberg, he sort of constructed this VG for this G semi-simple simply connected. And so for a group which is like semi-simple and simply connected, this is somehow the correct object that we want. And the point is that if you sort of just look at like the naive definition, which kind of generalizes Wimberg's construction, where you sort of do look at the Wimberg monoid, for instance, as constructed by Xinwen, then what you get is somehow, you know, not so nice in the sense that like you're sort of producing, let's say G simply connected is some cover. Let's see. Yeah, okay, you're sort of looking at the simply connected cover of some other semi-simple group. Then the thing that you will get, maybe I call it G prime, the thing that you will get here at the bottom is somehow related to with the top by sort of quotienting, being a sort of GIT quotient by this kernel. So let me just see, sort of kernel. So this will be sort of, sorry, what am I writing? So this Wimberg monoid for like this semi-simple group is going to be the sort of GIT quotient by the kernel of this map. And somehow this is not what I want. I don't want a GIT quotient by this group in the center, because somehow this makes this process of like quotienting by this, taking this GIT quotient sort of introduces like annoying singularities. The idea is that instead you should not work with this GIT quotient, you should work with maybe, let's call it a tilde version. It should really work with like the sort of Deligne-Mumford stack, which is what you get by looking at the actual stack quotient. So this thing is much better because like essentially the singularities of this guy is just the same as the one for the simply connected semi-simple cover. I don't want the one which is, you know, the GIT quotient, because the GIT quotient adds kind of singularities into the setting. So, I mean, we sort of work with this Wimberg monoid, but really like this stack version of this Wimberg monoid rather than the one, for instance, in the definition of Xinwen. Okay, so that's the caveat. But with this, so let me kind of say like what we have with this construction. Okay, this. Sorry, this is the wrong one. Okay, so what do we have? I mean, we're using this this like Wimberg monoid, this construction, like these isogeny models. So using this, we can produce like the space of like quasi-isogenies. So in the setting of like GLN, in the setting of GLN, there was this thing where you sort of needed to like divide by P. And the analog of what's happening in this Wimberg monoid setting is that you're going to be multiplying by an element of the center or by some element of T add. And what's the element of T add is going to be essentially the sort of longest root, the image of the longest root in T add. So maybe I should see, in general, like there is a map that goes from like, say, this VG lambda, I call it X, is it? What's the name? This X lambda add to this X lambda add, where you sort of add a root, so a co-root. So this a co-root. And this process where you sort of add this co-root is sort of similar in this, or at least it sort of translates in the setting of like GLN to the thing where you sort of allow yourself to divide by this power of P. So this corresponds, in some sense, I mean, you can make this more precise, into sort of looking at the space of like isogenies, kind of sitting in the space of like isogenies or quasi-isogenies with denominator, so at most say P to the H. So like this process where you sort of allow yourself, I mean, so this is just one copy, you just sort of add this like one co-root, but you can sort of first add like sort of any co-root, you can sort of consider the co-limit over all these kinds of sums of co-roots. So by analogy, if we consider the sort of co-limit over this process where you sort of sum over all over addition by this alphas, these co-roots, then what you get is what as a space that we call we get a space that this is going to be the space of like this stack is going to be the stack of quasi-isogenies. You get a stack. I'm going to call this Q isog over this BT, G mu infinity. So if you sort of take this co-limit over this construction, you're going to get a space that we sort of call this Q isog. And by this, by how we sort of construct this formalism from going from like an isogeny model into some space over this BT G mu, I'm going to sort of have two projection maps to this BT G mu, and I'm going to sort of get a stack, this Q isog over this. And this is what, or at least this is our candidate for like the space of quasi-isogenies over this like G mu aperture. So we say like a quasi-isogeny is going to be like some element of this point, and somehow like the idea is that, as you can see, like there's two maps back down to this BT G mu, and that's sort of roughly, you should think of that as like kind of like the source and the target of this quasi-isogeny. Like there's a quasi-isogeny between like the image of this P1 and the image of this P2. Okay, so that's the first thing that we get here. And of course, I mean like you should sort of check that this thing was not just like us kind of playing around and getting something nonsensical. So if you sort of consider now in the case where you sort of have a framing object, in other words, if you sort of choose a point, say this is a sort of this is a stack, this is a sort of p-adic stack. So if you sort of choose a say ZP Brever point of this BT G mu, so that sort of corresponds to choosing a framing object, then you can ask, like what is the what you get when you sort of pull back the fiber over this framing object. And so let me write the theorem that we have in this setting. So taking a fiber over some spurf point. So the theorem that we have is that what you get is going to be a p-adic formal scheme which is formally smooth over this guy. So let me just say, okay, so let me just say for all GB mu, where this mu is minuscule, this G is unramified, or this GQP is unramified, there exists, like the fiber, we can give this name, we give the name to the fiber, we call this RZ GB mu. So this is going to be a p-adic scheme, so p-adic formal scheme. It's going to be formally smooth over, and by somehow this formalism of like this relationship between this G mu, this F gauges and this crystalline realization, that you can sort of make this, you can sort of relate this construction, this F gauge, to the sort of underlying F crystal. You can sort of then evaluate this p-adic formal scheme on sort of perfect inputs. So where R is a perfect ring, what you see is that this is reduced special fiber, whose reduced special fiber is this affine Deligne-Lustig variant. Is the affine Deligne-Lustig variant. In particular, I mean, like this gives a sort of uniform construction, at least in the setting where like this, your sort of unramified group and your minuscule co-character of the Rapoport-Zink space. So this construction, for instance, like it sort of completely has no reference at all to like p-divisible groups. You're just kind of saying that like this thing, or like this case kind of like quasi-isogenies between like some sort of fixed G mu aperture, and like you're looking at a space of like all possible quasi-isogenies as we've defined it, gives me an object which is formally smooth and whose like reduced special fiber, or maybe the perfection, the perfected reduced special fiber is my affine Deligne-Dusch variety. So this is, of course, I mean, this is going to be the Rapoport-Zink space for this GB mu. So that's the first thing that we have, which is this construction of this Rapoport-Zink space. Okay, the next theorem is going to take a... Which one? Actually, should be the one, sorry. Okay, so that's the sort of local situation where we sort of have this, now we have this construction of this like Rapoport-Zink spaces sort of for all groups. We sort of, with no reference, of course, to like p-divisible groups at all. It's just this business with like G mu aperture. So, but of course, I mean, at the start of this talk, I talked about like the Shimura variety setting. So let me sort of explain in what settings that we can sort of globalize this space of quasi-isogenies when we sort of have this space of quasi-isogenies over the Shimura variety. Okay, so let me say that. I mean, that theorem, I think most of the details have already been written down. So this one, let me just say expected in the sense that there are still some details which I sort of haven't completely worked out yet, but I sort of strongly believe this statement to be true. So let's just let Gx be a Shimura datum. And you suppose that, I mean, I'm at sort of hyperspatial level. So I think like this, all this kind of setting, I assume that the group was unramified and I needed the existence of a reductive model for the group. So somehow this is all a sort of good reduction kind of situation. So it's not surprising that like somehow the level that I need is a hyperspatial level. Suppose that this K is like Kp, K upper P, where this Kp is hyperspatial. And that there exists a canonical integral model for this Shimura variety at this level. So let's say as Gx. So when I say here this canonical integral model, this is a canonical integral model, not in the sense of Moonen, but in this sense of this forthcoming paper of Keerthi and Alex. So canonical integral model here. So let me just say. So canonical integral model for me is that first there needs to be some relationship between this Shimura variety and this BTG object. So first is that there needs to be a formally a-tau morphism. Okay, sorry, I can't finish up. This is the last. So there is a formally a-tau morphism, this sort of symptomic realization from the completion, this p-adic completion of the Shimura variety to this BT stack. So I need that, but I also need not just that, but also a kind of extension property. So the extension property that if I'm looking at this, R is a sort of mixed characteristic DVR. and say F is a field of fractions, then like when do I get a point of the integral model? So I get a point of the integral model sort of exactly when the, so then x, let me just say, x in SHK. Okay, I'm just going to drop the gx. So SHKF extends to this integral model R exactly when the local system, so there's always a local system, okay, there's always a GC mu C local system over the Schumann variety. So it sort of extends exactly when this local system, when you sort of restrict it to this X, is crystalline. So exactly when local system. Okay, so this is the sort of canonical integral model that I want. So, but assuming that there is a canonical integral model, so let me say, sorry, I know I've run out of time, but let me just comment, like when do we know that there is a canonical integral model? So we know there's a canonical integral model in the situations where like P is greater than 2 and you are this pre-abelian type Schumann variety. So that's one case. And the second case is, of course, also the one that we wanted, which is this sort of for this P sort of quite large, this exceptional type Schumann variety. So let's say BST model. But here, we also need that, unfortunately, here I also need that this Schumann variety is compact. And this Schumann variety is compact. So that's the sort of situations in which I know that there exists a canonical integral model. So this pre-abelian type thing, or sort of with this very inexplicit large prime, and this condition that the Schumann variety is compact. But the point is that so with this, both these, with this assumption that there is a canonical integral model, then we can sort of globalize this result about the construction of quasi-isogenies. So we can sort of pull back and produce a global space of quasi-isogenies kind of sitting over the Schumann variety. So let me just say there exists then there exists a space that I'm going to call P, maybe Q-Isog. So some kind of formal, some p-adic formal stack that's sort of very similar to this P1 and P2. It sort of emits this map to the completion of the Schumann variety. And which is sort of formally related to the Q-Isog that's constructed there, sort of via pullbacks from this R-sim, via this symptomic realization, related to the global, the local stack. Yeah, pullback using this sin. And so that, I mean, sort of back to the starting question, which was this Igusa stack. So you can consider, I mean, the stack that you construct by sort of formally quotienting out, like the equivalence related that's generated by this PQ-Isog. So we can consider this, what we're going to call a sort of formal Igusa stack. That's sort of obtained by quotienting out this equivalence relation. So equivalence related. So generated by this PQ-Isog. And I mean, as the name sort of suggests, that it should have a relationship between the Igusa stack that Ming-Jia will talk about tomorrow, and also the Igusa stack, for instance, that sort of on the mod P fiber that, for instance, has been constructed by Qinwen. That appears in this paper of like Yang and Zhu. So like on somehow when you sort of restrict to like perfect inputs, you should sort of recover this construction of Yang and Zhu. And if you sort of restrict yourself to like this perfectoid, okay, I mean, if you sort of look at somehow like the sum associated diamond, then you should also recover this this Igusa stack, or maybe the sort of good completion, this good reduction Igusa stack that has been considered by Ming Jia. Okay, so let me just end here since I already ran out of time.